Hello, everyone, and welcome to this webinar covering XF's 7.9 release. I'm Naveen, and I'm an application engineer at Remcom, and I'll be giving you an overview of the latest features that have been added to Remcom's XFdtd. To start off, let me give you a brief overview of the presentation. Here are the specific features that I'm going to cover today with a brief demonstration of the features in the software as well. So the first two features are a post-processing feature, which allows users to combine the steady state results from an FDTD simulation to perform a post-processing analysis. And the next three topics involve talking about specific result types that users can use to uh, check the performance of the antenna arrays and also perform few specific type of analysis. And the last two features are mainly related to sharing the geometries within the teams in a company, the library bundles, and also sharing the CAD models or geometries between different companies by encrypting the design sensitive information. There is a GoToWebinar window wherein you can ask any questions during the webinar. My colleague Sam Seidel and Jeff Barney will be available to answer any questions that you might have. Feel free to type in any questions that you have in the questions window in the GoToWebinar. And also in the end, we'll have a question and answer session wherein I'll be answering any of the questions that have been not answered during the webinar. So the first feature that's released in XF 7.9 is the superposition. So this is a post-processing feature which allows user to combine any steady state results from a single FDTD simulation. So this offers any near field results that can be combined, E fields, H fields, B fields, the current densities, or even dissipated power, and also allows users to combine far field results as well. So here we have an example of a 60 gigahertz antenna array with 4 patch antenna elements. And as you can see, there are 4 patterns that are available. So each of these patterns are requested by first running in a FDTD simulation on this, wherein we request the S parameters and the steady state patterns. And the first pattern here is obtained by exciting the first element to the left. And similarly, 3 other patterns are available by exciting each of the individual elements. So this simulation would anywhere take between minutes to hours based on how complicated your geometry is. One nice thing about this is we can combine these results to get in a composite results of all the 4 elements active at the same time within seconds. So to the right, you can see here, now we have all of the 4 elements excited with equal phase and magnitude to get in a more directional pattern. And similarly, we can change in the phases between different elements to obtain different beams, steering it in different directions. And all these analysis can be performed in less than a second, which would greatly help antenna designers in designing beamforming antennas for 5G applications. So to look at the workflow on how we can achieve this in XFdtd. So once the project setup is done, users would perform an FDTD simulation on this. And in creating the FDTD simulation, we are requesting for S parameters and also specify the steady state frequencies at which we want the fields to be calculated, the near field and the far fields. And once the simulation is run, we get the results. And here in this case, we have an 8 element array with each of these antenna elements excited individually, and the patterns are available as seen here. To this, we can then add in, provide the power and the phasing for each of these elements to create a superposition simulation, which in turn provides a composite pattern with all of these elements active at the same time. Having looked at the workflow, now I'll show you how this can be achieved in the XFdtd 7.9. Here I have the same 60 gigahertz phased antenna array project loaded in XF. So this project contains 4 antenna elements, 4 patch elements here, as you can see in the project tree. So these are the 4 elements and contains 2 substrates, one in the lower, and below this is a ground plane. And we have one substrate on the top, which is hidden. And on this is 4 parasitic elements for each of these individual antenna elements. Each of these elements are fed with a modal waveguide, as you can see here. And I have requested the near field results, the steady state E fields on the planar sensor on the surface, and also have requested the far zone results. So individually exciting these elements, we can perform a FDTD simulation, which I've already done here. So once the simulation is done, we can access the results through the results browser. And here we have different result types that are available. And I'll quickly take you through the results, the near field sensor results, and also the pattern. So I'll first load in the results or the near field results. So these selected can be plotted on the geometry window, and I already have these loaded. And here you can see the E fields on the first element when it is excited, and similarly the E field distribution on the patch element when the second port is excited, and so on with the third and fourth element excited. And also have the individual patterns available for these from the FDTD simulation, which you can view here. So each of these patterns are corresponding to the individual elements. And I'll now show you how the superposition simulation can be performed on this. Before that, I'll unload all of these results. And to perform the superposition, we can get into the simulations tab and select the superposition simulation. Name it and create the select the input simulation which contains the steady state results, and then proceed on to add in a superposition simulation here. Here I would want to first excite each of these individual elements with a 0-degree phase shift, and this allows me to select all the active ports that are getting into part of this antenna array. And then clicking into edit superposition definition, here is where I can enter the different available power for each of these ports and also the phases. And I'll go ahead and create a second simulation here with a 90-degree phase shift and select all the ports and change in the phases for each of these elements. And once done, you can hit create simulation and you can see that the simulation is complete in less than a second. And these results can be accessed through the results browser, and each of the superposition created in the superposition tab results in a separate for zone results. And I'll have the gain plotted for this. So as you can see now, there are two patterns that are created as part of the superposition. This one is with the 90-degree phase shift, which tilts the beam a little towards 30 degrees to the left. And also, when all the elements are having 0-degree phase shift between them, we have the bore side pattern. And we can also combine the near field results. So I would like to show you the field distribution on the planar sensor for each of these simulations. So this now is the field distribution with all the elements of the array excited at the same time with different phase shifts and with no phase shifts between them. So the next feature that we have is another post-processing feature, which is array optimization, which again uses the steady state results from an FDTD simulation, which can be combined to obtain the maximum EIRP of an antenna array over a specified direction. Some of the use case that is supported for this feature include a phased array, wherein each of the elements are fed with different phases to steer the beam, and we would be obtaining the phases of these elements using the array optimization, and multiple arrays in case of a spatial diversity application where we run into multiple arrays to get a broader coverage, and a dual polarized antenna array and subarrays wherein you have a 4x4 array and would like to operate each of the 2x2 arrays of this 4x4 array individually for certain applications. Coming to the simulation workflow, it is pretty much similar to how a superposition simulation is performed within XF. Here we create an FDTD simulation, get in the results, but the step where it is a little different from the superposition is with the input. So here we provide the input directions, the azimuthal and the elevation angles at which you would want a maximum EIRP achieved for your beam. And you also provide in a set of allowable phases for the algorithm to optimize the best of these phases to give the maximum EIRP in the direction that you are interested in. And with that, we can get in the composite results. So let us quickly look into how this can be achieved in XFdtd. So here I have the same project on which I'll be performing an antenna array optimization. Before that, I'll quickly unload the results. And now I can perform the array optimization features, access the array optimization feature through the simulation tab, create the array optimization, and select the project with the steady state results from the FDTD simulation. And in the array definitions is where I'm going to define the ports which are part of my array. And here is where we select the amount of power that would be getting into each of the ports and getting into allowable phases. So we have a phase ranging from 0 to 360 degrees with a step of 5-degree increments. And these are the phases that we input to all of these elements so that the optimization algorithm can work on finding which of these phases would provide the maximum EIRP in the direction that you're interested in. And following this is where we define directions for your antenna array. And in this case, I would want to perform analysis on 3 different beams. So one is at setting phi to be 90 degrees and theta of -15, and the other beam facing at 0 degree of theta, and the last one at 15 degrees. So once the analysis definitions are set, we can go ahead and create the simulation. So as you can see, the simulation just took around 472 milliseconds to run for these three patterns, and these can now be accessed in the results browser and have the three antenna patterns which can be plotted. So as you can see here, we have three different patterns, and each of which is steered in a different direction and providing the maximum gain in the direction. So this one here is at theta of 0 degree, and similarly we have it steered a little to the left by 15 degrees, and a third pattern which is steered to the right by 15 degrees. So comparing the workflow between superposition and array optimization. So superposition, in this case, users are already aware of the power and phase that would be getting into each of the ports in your antenna array. And in case of an array optimization, the power and phases are not known, and the inputs are the directions and the allowable phases, and the phases for each of these elements would be calculated based on an optimization algorithm. So these two features coupled together would greatly streamline in designing any beamforming applications for 5G devices. Coupled with this is a specific result type, which is MaxHold. So usually we have a lot of numerous beams when we would want to analyze in case of a beam steering application. And one way to condense all this data into a single pattern would be to use MaxHold. So here we have antenna patterns generated for a 8-element array in 5 different directions, ranging from -30 degree to +30 degree. And the MaxHold result provides an envelope of all these 5 beams containing the effects of all these 5 beams in one. So as you can see in the 2D pattern, the blue line here is showcasing the MaxHold result for all of these patterns together. Using the MaxHold, we can plot the second metric, the CDF of EIRP. So the CDF of MaxHold. So this is nothing but a calculation which determines the peak EIRP level present at the maximum gain location of an antenna pattern, and also provides the possible coverage of the antenna for a given available power. So here we have 5 different beams, each of which are obtained through array optimization, and we found out the phases of each of these through the array optimization here. And as you see, each of these have relatively the same gain and also the same beam width. So in this case, plotting a cumulative distribution function of these 5 beams would look like these blue graphs to the right. So the blue lines on these are the CDFs of each of these individual elements. And as you can see, they're roughly the same because each of these are covering the same amount of space over for a device. And here you can see that each of these patterns have a maximum EIRP around 43 dBm. And if for suppose we have input power of 23 dB milliwatt, which is applied to these patterns, so roughly we have 30% of the pattern which is directed, and also shows that it's not doing that good of a job when compared to covering a much larger area. So using the MaxHold pattern, we will be able to combine the effects of all these 5 beams together. And now plotting a CDF of this function gives in the red curve here. And as you can see, for the same input power, we now have a much wider range that can be covered. Roughly 77% of the antenna, 77% of the angles are now covered with the beam steering capability. Let's look how this can be done, or how these results can be accessed in XF. So here I have the same project with 8 antenna array elements here, and each of these are fed with a circuit components, and this has a simple dielectric substrate and a ground plane, which is hidden right now, and this is the ground plane, and have the far zone results requested, and also have performed an FDTD simulation on this, and also an array optimization is done to obtain 5 different beams, and the results of the same is available in the results browser here. And I'm going to plot the gain of all these 5 different angles, or the directions that has been specified. And this is how the results look. So this is the gain pattern with at minus 30 degrees, and similarly we have a gain pattern at minus 15 degrees, and one at the bore side 0, and the other one at 15 degrees, and finally the last one at the 30 degrees. So a CDF plot can be plotted on each of these patterns individually and also on the MaxHold. So in the results, we have the MaxHold result, which can be easily accessed, and plotting the MaxHold for this pattern looks like this. And the CDF plot can be created by selecting the effective isotropic radiated power results and simply right-clicking and create the CDF plot. So I have created the plots for the MaxHold and each of these individual arrays, and plotted them in a graph here, which I'll be showing. So these results are very much similar to what we saw earlier. So each of the individual antenna array elements each of the individual beams have the CDF shown in the blue, and the combined pattern is shown in the red. So one of the practical applications for which this would be useful is finding out the coverage for a mobile phone which uses 3 different arrays. In the previous case, we have seen how numerous antenna patterns can be coupled together to form a MaxHold and plot a CDF for a MaxHold. In this case, we have MaxHold generated for each of the individual antenna patterns, antenna arrays. In this case, we have two 1x8 antenna arrays on the side, and one 3x3 antenna array on the back of the phone case, and we have a CDF plotted to each of these patterns. So as you can see in the black curve here is for the MaxHold results, which has been plotted for a 3x3 array, and also the blue one is the CDF of MaxHold plotted for the 1x8 array. As you can see, the array at the back provides a much better coverage than the ones at the side. But when we make use of another array on the side as well, now this is giving a 3D coverage for this device, and plotting CDF for all these three MaxHold combined gives us the results in the red to the right, which now shows that 93% of the antenna uh, pattern is covering a very large part of the angles that are available. With all these new features introduced, we have now renamed our naming conventions and also changed uh, our versions. So we now have XFdtd coming in 3 different versions: Standard, Pro, and MIMO. And all of the features related to the MIMO package, the superposition, array optimizer, and the circuit element optimizer are all now clubbed into MIMO package, and users who would want to use these new features would now want to register for the MIMO package. So the next specific type of analysis that we'll be looking into is the codebook analysis. So whenever we say arrays, it's not as simple as the ones that we previously saw, that those were just having 3 or 5 beam states which we would want to analyze. But in this case, if wherein we hundreds or tens or hundreds of patterns which we would want to analyze, then we provide a custom script, a post-processing script, which can now plot the MaxHold result for all these patterns. So the workflow is pretty much the same. We create an FDTD simulation, and following that request the FDTD results, and perform a superposition simulation, and provide a codebook which is in the CSV file format right now, and then plot in the MaxHold results for this particular set of data provided in the CSV file. And I'll demonstrate how this can be done in XFdtd. So I'll first unload the previous results, and to have the codebook loaded into the software, we would first want to create a superposition simulation. And we can just have one of these simulations kept as is, or just create a new one. And once this is done, we can access these results again from the results browser and have it plotted it for you. And we just want one of the results from the superposition simulation to be selected, and now we can just load in the codebook, selecting the appropriate frequency and browse in the CSV file. So to quickly show you how this looks, have it open, and this is how the codebook format looks. So the codebook now contains the magnitude or the power for each individual ports. The first row selected, the first column selected has all the power that we would want to input to the first port. And next we have the phases, and in the same fashion we have the power and phases that are getting input to each of the individual elements. So now when loading it, I can also select the target graph. In this case, I would want a new graph, and then click OK. And now you can see that the analysis is being performed really fast. And we have a lot of beams that can be tracked, and an array optimization and a MaxHold can be performed on this. So once the simulation is done, now we can get the CDF plot for all the different beam states that were available in the codebook. So this is how the CDF looks like. The next feature that we have is the power density. So along the lines of SAR for lower frequencies, we have power density for frequencies greater than or ranging between 6 gigahertz to 300 gigahertz. So we have the latest version that was released in the end of 2019. This draft is not finalized, but XF is consistent with the most recent draft of the standard, that is the CDV, and users can contact us if you're interested in evaluating the power density for planar surfaces. And we'd be happy to extend the power density scripts uh, if anyone is interested. The last two features that we have are the library bundles and the object encryption. So 7.9 now offers a bundles capability with our libraries, and that allows us to take an array or multiple or a mix of parts, components, and materials, bundle them together and store them in the library. Whenever they are pulled out of the library, the references and relative positions are maintained in the same way as we put them in, so which would allow us to share geometries or objects more easily with our team members. This couples with the object encryption feature. If you want to share the project with other people, another company or team who don't have authorization to review your designs, then you can encrypt geometry, material definitions in order to protect it. So I'll show you how these two features can be accessed through the XF. So here we have a sample project with a PIFA antenna with the ground plane and a small substrate. So this is the antenna, and this is connected to the ground with the circuit component here. And if you wish to share this model with someone and would like to still retain or not show the sensitive design related information to them, you can quickly do so by hiding the geometry. And for that, we can set these to be invisible, and also the component. And just for the sake of knowing where exactly the feed is, we have a cutout which is formed, so when sharing this model, the other person can know how exactly to align this particular chip with his CAD model. And we have a bounding box that is created within which the antenna is enclosed. And now to encrypt this, we can select in the required component definitions, the geometry, the material properties, and encrypt them with a simple password. And now all of these informations are related to the material definitions will not be available. So only if a person has a password can get to know the definition information or even anything related to the geometry. You can have this shared between different people by just clubbing them together into and storing them in the XF library. And for that, I'll create a sample library in XF. And drag in all of these into the library and create a bundle. Now we can share this to someone outside the organization. And if he were to open the same project, he would not be able to access any of the sensitive information related to the design. So he can do so by selecting the library and loading in the bundle. And as you can see here, uh, we have the antenna available, and we have the cutout, which gives the information to the user on how to align this geometry and where exactly the feed is located. But he doesn't get any other information related to what materials are being used, what are the mesh properties, and all of the results related to these uh, or the outputs related to these geometries are also encrypted and will not be the mesh related information will not be available to the user who is trying to use this geometry in his CAD models. With that, I've covered most of the features that we have uh, added to our most recent version, but these are not all of the changes. We still have many usability, scripting, and performance related updates that have been added to this version based on the requests from users like you. To get more information related to each of these features and the other updates that are available for 7.9, users can look into our support site uh, to get more information regarding this. With this, I'm done with most of the demo part and showing off of the features. And uh, now I would like to open up for questions, and feel free to like ask any questions through the chat window. And let me quickly look into the questions. So there is a question. What algorithm is used for encryption? So XFdtd uses a combination of obfuscation and encryption to allow geometry to be shared for simulation without compromising the inner workings. So all files written out are fully encrypted for protection. And coming into the particular algorithm, so we mainly use, yeah, I think uh, I can get back to you on that. Uh, I would consult my development team, and I'll follow up with you shortly after the webinar. And we have some other questions here. Uh, what file formats do you support for the codebook script? So currently we support CSV format. However, if you wish to customize the script, we can do that for whichever format is interested that you're interested in. And the next question, can superposition be used for other applications? Yes, it can be used for different applications. Some of the common applications are MRI and filter design, and it can be used for anything that uses FDTD simulation to compute S parameters and steady state results. So there is another question. Are these features available after version 7.9? Yes, all of these features are available from 7, and uh, particularly under 7.9, it's the mmWave package that you would want to uh, look for to use these features. And there is another question. On the cell phone, can you model the effect of the hand that holds the phone? Uh, yes, we can do that. And there is another question. Will the webinar material be shared as document for future use? We would not be sharing out the slides, but we would definitely be sharing a copy of today's webinar shortly, and that is something that will be accessible. So there's another question. Can we download trial version of the tool? Uh, if you need the trial version, you would want to get in touch with the account manager, and they will be able to set you up for a trial version. Uh, there is another question. Can I know how to simulate PD in detail? Uh, yes, you can. I mean, we can do that. I mean, we can get in touch with you after this webinar to give you more details of how you can simulate the power density in detail. And in continuation to one of the questions who requested for trial, so we do have a form that you can access through our website, and you can fill in the details to get the trials. And yes, there is another question. Can video be shared? And it's much better to understand than slides. Yes, we will be providing the video of today's webinar shortly once we're done. So we have, I think, most of the questions answered here, and any of the questions that have not been answered, we'll make sure to follow up with you on that. And this brings us to the conclusion of today's webinar. I would like to thank everyone who've attended this webinar, and feel free to get in touch with us if you have any more questions related to the latest features that have been released, or the trials, or any information that you want to know related to the custom scripts that are available. So feel free to contact us, and also you can find more information on our support site. And that's it. And we look forward to know anything that you learn from the features. So feel free to contact us with any of the feedback that you might have. And have a nice day, and thank you for attending the webinar again.